So let's take a look at trigonometric substitution. On the left here we see the integral of square root a squared minus x squared. And you see two others, and they are both the differences between a squared and x squared, or sums. And now, the key idea here is that when you try to integrate this, it's not going to be straightforward to do. It's going to be quite hard. And going reverse and trying to anti-differentiate an x squared term inside a square root is not easy at all. So, to make our lives easier, we convert this into a trigonometric substitution. And now, what that allows us to do is, for, let's say, a squared minus x squared, we let x equal to a sine theta, and then we input that into the integral. We simplify this integral into a cos theta, and it becomes very, very simple to do. And this is the key idea about trigonometric substitution. Same thing here. If it's a squared plus x squared, we let x equals to a tan theta, for which it simplifies into a secant theta. And if it's x squared minus a squared, we can let x equal to a secant squared, or secant theta, and then it simplifies into a tan theta. So let's take a look at an example problem. So part A says, show that the substitution x equals 3 sine theta gives square root of 9 minus x squared equals 3 cos theta, and dx equals 3 cos theta d theta. So this one is pretty straightforward to do. All we have to do is substitute this x as 3 sine theta, so this becomes 9 minus 3 sine theta squared, for which this equals to 9 minus 9 sine theta squared. And this is going to be equal to 9 times 1 minus sine squared theta, for which this turns into square root 9 of cos squared theta, and that equals to 3 cos theta. So that proves that right there. And dx equals to 3 cos theta d theta is purely derived from x equals 3 sine theta, where d of x over d of theta equals to 3 cos theta, and therefore d of x equals to 3 cos theta d theta. So that's it. Part B says, hence evaluate the integral of x squared over the square root of 9 minus x squared. So in part A, we already kind of derived everything. So x equals to 3 sine theta, so I'm going to input that in. And the square root of 9 minus x squared was equal to 3 cos theta. And dx was equal to 3 cos theta d theta. So that's what we have to evaluate here. The 3 cos thetas cancel, so we are left with 9 sine theta squared d theta. And I'm going to extract this 9 here. And integrating sine squared theta is not as easy to do, so what I'm going to do is actually convert this into cos 2 theta, using the identity cos 2 theta equals to 1 minus 2 sine squared theta. And isolating sine squared theta equals to 1 minus cos 2 theta over 2. So that's what I'm going to input here, and I'm going to make these separate terms just like that. And this is going to be equal to 1 over 2 theta minus 1 over 4 sine 2 theta, and of course the plus c. And now we have to input back the theta in terms of x. So if we see our original expression that x equals to sine, or 3 sine theta, I'm going to isolate theta by saying that this is the arc sine of x over 3. So we can quickly finish this off by inputting this arc sine x over 3, just like that. Now you could go ahead and continue to simplify this, but that would just make the video longer unnecessarily, so you can go ahead and do that yourself. But this is how you use trigonometric substitution to solve integrals, just like these.